Determine a vector perpendicular to two given vectors. So we have two given vectors here. What they're asking us is for a vector that is going to be perpendicular to both of them. So we're looking for one vector that's going to cut both of them at a 90-degree angle. So we're in 3 space here somewhere. In fact, they've given us 2 points. This vector needs to be just one single vector. And due to our dot product, we know that we're going to call this perpendicular vector vector P. Okay? And what we know from this is that A dot P, if they're perpendicular, is going to be equal to what? Yeah. And A dot B, if they're perpendicular, is going to be equal to what? Good. So, I clearly have no idea what the values of vector P are, so I'm going to represent them with variables. Okay. Any given value on the x-axis, I'm going to call it x. Any given value on the y, and any given value on the z. So I'm going to represent vector P with x, y, z. I'm then going to plug in these values of x, y, z into our dot product we had above. So, what that means now is vector A, which is 1, 5, negative 1, 1, 5, negative 1, dot vector P, which is our x, y, and z, is equal to 0. And the same holds true with vector B and P. Vector B, which is negative 3, 1, 2, dot x, y, z, is equal to 0. Okay. So what we're going to get is we're going to get a bunch of equations, essentially, when we go to figure this out. We're going to find out that the first one here are 1 times 5, sorry, not 5, 1 times 1 times 1, oh, sorry. So our 2 equations, I'm not sure what I was looking at there. Okay, our first equation we're going to get is 1x, because remember, we add these together after we multiply them. So we get x plus 5y minus, well, technically plus, but I'm going to say minus because negative 1 times z is going to give us negative z, is equal to 0 in this question. Okay? And in our other one here, we're going to get negative 3x plus y plus 2z is equal to 0. Okay? We're then going to try to verify this or set them equal to something here. We're going to try to solve for what either x and y could be. So we're going to take we can do substitution. What they've done in the book is they've done some elimination to solve this. Multiply equation 1 by 3. Equation 4. Okay. So, we'll do substitution. Essentially, if I bring z to the other side of this equation, I can find out that x plus 5y is equal to z. And I can plug that into our other equation over here and then solve it. So this is our equation 1 and our equation 2. So we'll get equation 2, negative 3x plus y plus 2 times, and we're plugging in this value instead of z in the other equation. X plus 5y is equal to 0. Okay. From there we get negative 3x plus y plus 2x plus 10y is equal to 0. We're going to get all the x variables on one side, all the y variables on the other. So we'll have negative x minus 11y. In other words, x equals 11y. Did you guys get that? Does that make sense? 3x plus negative 3x plus 2x is negative x. Y plus 10 is 11y. When I move to the other side, it becomes negative. We get positive x equals 11y. I can then take that and put it back into either equation 1 or equation 2 to get either y in terms of z or z in terms of y. So we take this value and we plug it into here. So our equation 1, we will get 11y. So I've replaced the x with 11y plus 5y minus z equals 0. And if I just move z to the other side, z is equal to 16y. So we have now replaced z and x in terms of y. Good. Okay, so we can now plug these values in for our other equation. So what we've now done, let's highlight where we were, is we now have x in terms of y and z in terms of y. Okay? So we can now replace our component. We know exactly what these are going to be when we go to plug them in. We can set up components of our, was it p I had? P. Okay. So our p variable here, or our vector p, is going to be equal to the x value being 11y, y value being y itself, and the z value being 16y, which means because we're in 3 space, there are an infinite number of vectors that can be perpendicular to this. So we're going to find vectors and numbers that multiply into this that can do any scalar of this vector here. Okay? Let me pause. So because we have our vector p being any number given a vector, as an infinite amount of them, we have our variable y. So we can plug in any value of y in this case. What we're going to say is this is kind of like a scalar of the number. So instead of calling it y, because y usually represents a specific point on the graph, I'm going to say let y equal the scalar, what do they have in here? T. Okay. So what that means is I can factor out the t in this. So our vector p is also the equivalent of 11t, t, 16t. Well, I can factor out my scalar of t, and we know our component is 11, 1, and 16. So what we've just found is this component point here, this vector, any scalar of that will be perpendicular to the 2 vectors that we originally started with. And we can test this out by essentially plugging in any value for t to solve for this. And what we'll do is we'll take our 2 original numbers and we'll plug them into the scalar of it. So our very original one of vector A was equal to 1, 5, negative 1. Okay. And remember, this is a perpendicular vector. So what scalar of these numbers would you guys like to use? What number would you like to use for t? 8? Okay. So assuming a scalar of 8, we know that our dot product of A and P is going to be equal to what? 0. They are perpendicular to each other. Okay? We just got to know that our product P has a scalar of 8. So this is just a proof right now. We're just proving this. So essentially we have 88, 8, and 128. Well, I want to check that. All right, 128. Good. So we're going to take these values. Our A again was 1, 5, negative 1. Dot 88, 8, and I'm gonna need you with the calculator to help us out here. is equal to 0. We just need to prove that this is perpendicular. So we get 88 plus 40 minus 128. Oh no, this works out very easily. 88 plus 40 is 128. Minus 28 is equal to 0. So, even with a different scalar other than 1, 2, 3, we just chose a random scalar of 10 for this question. We're able to prove that that component with any scalar of that vector, it would be perpendicular to those two vectors. Okay, so any scalar of the vector we found, 11, 1, and 16, would be considered perpendicular to the two vectors that we originally started with.